Hello everyone, welcome to our videos. Today we are going to talk about the Automotive Key Management System, which is a very fascinating and a critical topic in automotive cybersecurity. While it may seem straightforward at first glance, it is a highly complex and essential aspect of the security. To guide us through this in-depth discussion, I'll hand it over to my colleague Dharmesh. So, Dharmesh, let's get started.
Yeah, before we talk about the key management system, let me walk you through the importance of having it in automotive industry. In real world attack part would be much more complex, but whatever you are currently seeing, it is simplified version on the screen, so it would be easy to understand the scenario. So as you know that in today's modern car, we have a lot more functionality and advanced features involved. So more than 70 to 100 issues are involved in the architecture of the vehicle. That's where this all the functionalities are fulfilled. Nowadays, very convenient features like connecting to the internet, apps or mobile phones, automatic payment systems. So such kind of features would require the interaction to the outer world, and that's where the problem comes. So majority of the cyber attacks are happened via the remote access. We also discussed this in our previous video where we went through the report. So in that published report, we seen that almost 75% attack happened via the remote access. So in the image, you can see that the first attack part for the attacker would be to gain access to the car network via remotely connecting to infotainment issue. So once an attacker attacks somebody who has, let's say, good experience in this particular domain and also have the advanced industrial tools, then as an attacker, he can be get access to this infotainment system, have a good foothold on the infotainment system to gain access to the remaining issues within that particular network. So for example, here, let's say as an attacker, he would gain access to the engine control unit, so engine control issue, and he can, for example, could able to flash the malicious or tempered software firmware to the this particular engine control issue. And once this message got means issue got modified, the message what he want to send, he can manipulate that. So for example, there is a message going from engine control unit to the acceleration or increasing or decreasing, and driver is driving on the highway, and suddenly the message would be like put the brakes uh, on the wheel, then that could lead to the accident. So there could be endless possibility. Once the attacker gets the access to a particular component, he can do based on the motive. He can affect the driver, passenger, etc. So yeah, if we knew that these are the attacks can be possible, then can't we do something about it? So the answer is yes, we can prevent this. So generally, in this video series or past whichever the videos you are following, we generally talk about the mitigations, or I would say cybersecurity controls or measures. So generally, as a cybersecurity engineer, the cybersecurity architecture what we follow is the layered architecture. So you can implement the different cybersecurity mitigation at different level, starting from the higher level to the issue level. So in this example, let's see that what are the cybersecurity measures we have identified. So to prevent the access, easy access remotely to the infotainment system, we can establish the TLS connection. By using this, it would be much more difficult to gain access remotely or communicate from remote access to the infotainment issue. We can also add the reverse engineering protection at the issue level itself to make it harder for reverse engineering the code for that particular issue. And we can also implement the secure boot. So secure boot is basically it will ensure that only the authentic firmware would be executed at particular the time when the issue starts up. So that will ensure that there is no tampering happen. And we can also prevent the ongoing messages that this is coming from the authentic source. We can also implement something called SECO secure onboard communication. So by implementing these features, we can avoid this cyber attacks or whichever the path we had identified by implementing this. So as it's depend on the use case and resources available, you can implement at different level. So this would be if implemented at every layer, then it would be much more difficult than when we don't have any mechanism.
So, what is reverse engineering protection here?
Let's say if attacker gain access of this issue and this issue firmware, he could able to let's say decrypt the data or reverse engineer what's happening in this issue or what are the messages he can send from this issue to other issue. So the firmware itself for this issue, until and unless, let's say, we don't have encrypted secure firmware stored or some protection, in that case, it would be difficult to reverse engineer. But if we don't have any protection, he could able to use some tools and reverse engineering the firmware. Yeah. Then uh, on the screen, you can see the some of the common cybersecurity controls available. So first one is the secure software updates. So basically, whenever the software is flashed, we'll have something called code signing. So using the digital signature, you could sign the code before you actually flash it to the issue. So here, if you see the root of trust, so there are two things. One is asymmetric keys. So it's depend on your implementation. You could use the symmetric keys. So use the single key or asymmetric public private key for the implementation. Here also you could use the X509 standard digital certificate to do the code signing. Uh, One more is the diagnostic hardening. So as in our previous video, we discussed about two cybersecurity relevant services available. Service 27 in the diagnostic and service 0x29 uh, for making diagnostic communication much more secure. We can use the TLS for transport layer security. It's basically the widely adopted security protocol, basically to uh, make sure that these handshakes happen properly and whatever the communication over the internets happen or remotely happen is happen securely. We also have secure boot, so where actually before you run the software, so secure boot will check the authenticity of the bootloader and application before running the software. We have the SECOC for the secure communication between the issue. We also have some reverse engineering protection. So as you can see, the last column here, the root of trust, we have some kind of cryptographic key involves to achieve this cybersecurity controls. So whenever these cybersecurity controls are implemented, one thing is common that you require the cryptographic key. And once you, let's say, lost this key or somehow the key itself is being stolen, in that case, whatever the implementation you do would go, I would say, waste. So it is very critical and important to uh, s- make sure that these keys are securely stored or securely generated, etc. And that is why today's topic comes, like how does this vehicle key management's life cycle present in automotive system. So before, yeah, we talk about the cybersecurity key life cycle in automotive. Let's see what are the different types of cybersecurity keys available in the automotive system. So first one is the development keys. So purpose of this kind of keys are used in the issue development and the testing life cycles. So basically, for example, a team at the OEM like Boss is developing a new ABS issue anti-lock braking system. Then this team would be requiring cryptographic development key to flash, test the firmware, debug it, and simulate the different braking scenarios. One.
Don't take company names.
Okay.
Can
Yeah.
the tier one OEM can use.
Okay. Yeah, I'll come again then. Yeah, for example, a OEM development team is developing a new ABS system issue, anti-lock braking system. Then the development team of that OEM would be requiring the development key to flash and test the firmware, debugging, and also the simulate the braking scenarios. One more example would be a startup who is working on the EV battery management system. So they would require the same key across all the prototypes for quick iteration and testing. So some of the key characteristic, if we see about this development keys, are like it would be mostly same for multiple issues or OEMs, which is not so secure. It is shared across the team and it would be accessed locally. So that is one disadvantage, but the advantage would be it is you don't have to generate multiple keys. You can use and the internal purpose and quickly you can do the development. So that's where these keys are placed. The second type of keys would be the infill keys. So the purpose of this kind of keys are providing the secure access to the customer vehicle. For example, diagnostics, recall, or OT update. For this particular features, we would require the keys, and these keys are called the infill keys. For example, when your OEM whichever OEM car you are using, which will show that check engine lights are turned on. So when you go to the repairing shop, the dealership uses an infill key, which is linked to your vehicle identity number to diagnostic the particular issue and see what is happening. So yeah, we also see that many OEMs are providing OT updates. So each car's issue verifies the update using its unique key before installing it. So some of the key characteristic, if we talk about this infill keys, are like it is unique per issue and it is linked with your vehicle identity number or serial number of the issue, etc. And this key can be accessed via cloud with the OEM authentication. And the third type of keys are the one which is the plant key. So purpose of this kind of keys is used it only on the production line. For example, flashing the firmware during the assembly line. So for example, infotainment system from any OEMs is getting developed. At that time, a plant key unlocks the issue for firmware injection and then permanently locks it for the security purpose. And some of the key characteristic of this kind of keys, if we talk about, then would be like it is short-lived, or we can say one-time usage. So only in the production it will be used, and once it is used, secure unlocked for the manufacturing, then it will be destroyed. So I think, yeah, these are the general different kind of keys available in the automotive industry. So as you can see, there are different kinds of key, and also we see how it is important. So that's where the life cycle management comes. So automotive cryptographic key management life cycle, if we see it on the screen, you can see in the image there are different steps involved, starting from the its generation of the key to the destruction of the key. So it involves the provisioning, usage, rotational policy, revocation of the keys, etc. And these steps are recommended by the NIST standard, NIST 857 standard, where they have recommended that these are the steps should be present when you do the key management. So we will be discussing each of these steps in detail in coming slides. So we can first start with the generation. So we'll start with the cryptographic key generation in automotive system. There are three primary methods for generating cryptographic keys in automotive systems. One is centralized authority. So here the OEM or supplier generates and also stores the keys, ensuring the uniformity, but this requires the secure distribution. The second would be the issue generated. It means that the individual issue, electronic control issue, creates their own onboard keys, offering the flexibility but demanding the robust entropy sources. We'll come to entropy sources in a bit. The last one is the negotiated keys. So here the issues collaboratively derive the keys, such as during the TLS handshakes, balancing the security and scalability for dynamic environment. So I mentioned about the entropy sources. So entropy or randomness is a vital for secure key generation. So higher the entropy is, means that stronger the key is. So there are two main types of random number generators are available. One is true random number generator, so which is more relies on the physical phenomena like voltage, noise, or temperature, something like that. So making it non-deterministic and highly secured, I would say. So it's ideal for the critical task like secure boot, but it is costly and slow, I would say. And the second type of generator would be the pseudo random number generator, which uses the algorithm and seeds, making it deterministic, less secure. However, this will be fast and cost efficient, and this is suitable for the task like secure diagnostics or session control keys. So depending on the use case, what you have, and selection of this random number generation will depend on the factor like how much costly solution you want to develop, or which feature you want to implement. So you can choose your random number generator accordingly. So now let's see about the distribution of the keys. So how key distributions are happening in automotive, since we have different kind of keys available. So key distribution methods can be broadly categorized into symmetric and asymmetric, which is also a public key distribution approach. So first one is the symmetric key distribution. So here a single shared key is used for both encryption and decryption. While it's efficient, it poses some challenges in securely sharing these keys between the two parties. So there are two methods available for sharing it. So one is the pre-shared keys, PSKs, and the key agreement protocol, uh, DeFi Hellman method. Now, a preset key is symmetric secret key manually distributed to all the parties before secure communication begins. So it's commonly used in the constrained environment, for example, IoT devices or automotive issues. The same keys is pre-installed onto the device, uh, for example, issues during the manufacturing. Uh, so yeah, this is the PS case. And whereas in the key agreement protocol, Diffie-Hellman method, so the information shared between two parties are usually on the unsecure channel. However, it is not the exact information shared between two parties. It would be like modified the information. So if we discuss this with an example, so let's understand that uh, two persons, person A and person B, wants to share a secret color. Color is brown to each other. Now both person publicly agreed that first they'll send the yellow. So now person A has the red color. He will mix it with yellow and send it the orange color to person B. Now person B would have let's say blue color with him, then he will mix it with yellow and sends the green color to the person A. So once they receive these colors from each other, again they will mix it with their own color. So person A would mix red with green, then he will get the brown. And similarly, person B would mix it color blue with color orange, then he will get brown. So here you can see that both the parties, ideally they don't directly communicated the brown color, but they got the private secret key in this case. So this is how this Diffie-Hellman method works. So yeah, this is the symmetric key distribution. Where we comes to the asymmetric key distribution, so here public and private keys are in pair, and this is used for encryption and decryption. So generally public keys are the one which is set publicly. So now what are the different methods to distribute these keys? So one is like public announcement, where user broadcast their public keys openly, for example via website, forum, or emails. So there is no central authority to verify these keys. The second distribution method here is the public directory. A trusted organization maintain a centralized directory like a phone book listing user public keys, and these keys are updated periodically. The third one is public key authority. So a live central authority dynamically verifies and distribute the public keys upon the request. It's like call center, so it will be 24 by 7 help desk. uh, you can understand like that. And the fourth one would be the public key certificates, PKI. So a certificate authority would be issuing the digital signed certificate binding the public keys to identify uh, the particular source or party. So this is the broader way how the normally distributions happens for the cryptographic keys. Now, the third one is we'll discuss about the usage of the secure key in automotive. So secure key enables three core functions. The one is secure communication, so encrypting the data between the issues over any communication channel, CAN or Ethernet, to uh, basically block the manipulated or wrong messages or spoofing kind of attack. The second function would be to firmware authentication, so ensuring the only signed or trusted updates run on the issue. And the third function would be protected diagnostics, so safeguard the diagnostic interfaces like UDS from malicious access. Uh, so y- Here you can see in the image what all are places the cryptographic keys are used in current modern vehicles. So you can see the overview of vehicle network architecture. So issues like powertrain, ADAS, or body control modules connect communicating via the central gateway issue, and externally the connectivity to the gateway issue will be to the cloud or remotely connected via Wi-Fi or cellular tower. Uh, so or we can also have the interfaces like OBD2 ports or smartphones are connected by USB. So these are the key places you would say that where the cryptographic key are generally stored. So it's starting from the lower level, issue level, to the higher level control modules, and then the gateway issue level. So every place based on the features, we would require the usage of these cryptographic keys. So imagine your car is encryption keys are like a lock of your front door. Then would you use the same key for let's say 10 years? So yeah, of course not. So in that case, the next point comes uh, how this key rotational, or why this key rotational policy is required. So we'll explore the key rotational keep vehicle more secure. Uh, so nowadays we see that lots of cyber attacks and threats are coming up. So that's where key rotation becomes very important. So there are mainly two purpose why we require the rotation of the keys. One would be to risk mitigation, which will be like protecting or reducing the expose of brute force attacks or key leaks. For example, a hacker interacting the CAN bus traffic uh, can't decrypt the old message if the key are already regularly changed. And second, it is why we need to rotate is because of the regulatory compliance. So standards like UN R155 mandate key rotation to ensure the vehicle cybersecurity. So let's compare three key rotation method. One is the time-based rotation. So key expiry on the fixed schedule. For example, annually or every 2 years, the key would be rotated. Uh, Automotive use case would be like infotainment system rotates the key yearly to protect the user data. Uh, Second one is event triggered rotation. So immediate key replacement after some security incidents happen, or is there a hardware change. So in that case, you would require the event trigger rotation. So after an issue replacement or OT update pushes a new key to the uh, issue to maintain the trust. And the third approach would be for the hybrid approach, where you will combine the schedule and event driven rotation. So telematic unit uses the time based rotation, but immediately any updates is needed, then update the key via the OTA to prevent the further breach also can be done. So it's depend on the use case. This approach would be selected. Uh, and next would be, let's imagine that a single compromised key could let hacker disable, break, or steal the vehicle remotely. So we will examine how this emergency key revocation acts as the emergency brake for automotive cybersecurity when the threats emerge. So when to trigger this revocation? So here also there are two aspects. One, key compromised. So if the factory key leak during the manufacturing, so revocation is required to prevent the mass exploitation. And second one is issue decommissioning. So critical when scrapping the vehicle to prevent the again somebody cannot use reuse these keys to gray market the issues. So these two are the I would say purposes where we would require the trigger of revocation. And if we think about like what are the different mechanisms for revocation of the keys. So the first one is the CRL, which is certificate revocation list. So how does this works is like certificate authority CA publishes a blacklist for untrusted keys. So for example, EV charging station checks the CRLs to block the revoked charger certificates. This is how the CRL works. Then the second mechanism would be the OCSP, which is online certificate status protocol. So in real time querying to certificate authority to verify the key status, like background checks for the keys will be happen. So for example, dealership tools uses this particular mechanism OCSP during the diagnostics to ensure that only authorized access is there. And the third one would be the local key invalidation. So here issues are programmed to reject the specific keys so via the secure firmware updates. So there will be a particular keys or some kind of range where you said that okay, if something try to use this, then straight away reject it. So safety critical systems like airbag system or ABS system immediately drop or revoke the key to prevent the life-threatening hacks. So in 2020, Tesla used this OCSP, uh, online certificate status protocol to revoke almost 50,000 keys after a supplier breaches, preventing the fleet-wide attacks. So yeah, that's why it is important to have some kind of revocation mechanism uh, already in your process and also implemented.
So I have a question here. Is there any standard that impacts the life cycle, the key life cycle management system?
Mhm. Yeah, that's the good question. So yeah, we discussed in the key rotational policy. So why we require the key rotation? So there we had one point which state that the automotive security standard like regulations UNR 155, which makes mandatory requirement that you should have key rotation in place. So also the R155 specifically tells two requirement. Article 5.2 which mention about the secure key storage, and Article 7.2 mention about the revocation mechanism. Also, it's just described about the audit trials for the key changes whenever it's happen. So that's why it is mandatory to involve these steps in the key lifecycle management.
Then one more question. How are the cryptographic keys managed for the third-party diagnostic tools or aftermarket ECUs without compromising the security?
Mhm. Yeah, that's a good question. So, yeah, to answer your question, if we see it's OEM controlled access, so time limited certificate issues to the authorized repair shops, and the J2534 pass-through device enforced key-based authentication is provided. So here J2534 pass-through is the standard defined by the SA Security of Automotive Engineers that provides the standardized interface for reprogramming the vehicle control units issues, allowing the independent repair shops access to their manufacturer level software updates via the diagnostics tool. So there they have clearly defined the strategy, or let's say the standardize to how to fulfill this pass through. So using this, we would say that it would be secured, that this won't be compromised. But yeah, in some incidents, it could happen that the spoofing of this tool itself with advanced technology could happen. But yeah, with following this standard, I think it will take care that it is followed properly, and the third party diagnostics tool or aftermarket issue without compromise their security. Thanks all for joining this session, and please do like, share, and subscribe our channel for getting the upcoming videos, and stay tuned on the similar kind of knowledge updates. Uh, Thanks, and see you in next session.